Okay, we're going to look at oblique impact of a sphere on a plane. So, recap on coefficient of restitution. So we're looking at a sphere hitting a plane and bouncing back off again. E is equal to speed of separation over speed of approach and takes values between 0 and 1. So that's perfect inelasticity to perfect elasticity. And we're only considering a smooth sphere and a fixed surface. So the surface won't move when the sphere hits it. And the sphere may be modelled as a particle, so we don't need to worry about spin and that sort of thing. So it's just keeping those modelling assumptions quite simple. So we have a fixed surface and a sphere bouncing off it, and we can split these speeds into vertical components perpendicular and parallel to the plane, so that this is u sine alpha, u cos alpha, and here I've got a v cos beta, v sine beta. We need to bring impulse into this, and because the surfaces are smooth, the impulse is going to act in a normal direction to the plane. So that's the impulse acting. And then the other thing to think about, I think this is quite obviously, but you do get a change in momentum when you've got a sphere hitting a fixed surface. Momentum's conserved in collisions, but not when you're hitting a fixed surface, because some of that energy gets absorbed. The impulse on the sphere acts perpendicular to the surface, so we've covered that. The component of the velocity of the sphere parallel to the surface is unchanged. So because the impulse is acting perpendicular, it doesn't have an effect parallel to the surface. And so velocities parallel to the surface remain unchanged. And so u cos alpha is equal to v cos beta. Perpendicular to the surface, we can bring in restitution. And so E, coefficient of restitution, is the speed of separation, which is v sine beta, over speed of approach, which is u sine alpha. So we're dealing with speeds, not velocities here. And so that's our little formula for restitution. And the angle of deflection, so this is the angle through which the path changes. And if you think about this, if you extend this line here down, then this angle here is alpha. And so the angle of deflection is alpha plus beta. And then one other thing to note, and this comes from here. Oops, sorry, I meant to say note. So if I multiply by the denominator, v sine beta is equal to EU sine alpha, and u cos alpha equals v cos beta. So we can divide through this side by cos beta, and this side by u cos alpha. So I just realised I forgot a v there. And so these v's are cancelling, these u's are cancelling, and tan beta equals E tan alpha. And we know that E is between 0 and 1. And so tan alpha is greater than or equal to, tan beta. So that when you multiply by something a little bit less than 1, you can get tan beta. And if tan alpha is greater than or equal to tan beta, then alpha is greater than or equal to beta, because this angle is between 0 and 90. And so this angle here is always going to be less than or equal to alpha. So just something to think about. It's sort of intuitive, but you can see it with the maths there. So that's kind of the key things you need to use for oblique impacts, and I'll go over a couple of examples on the next video.